In this lecture, we consider our solar system. We have to learn as much as we can from the closest examples of planets and their moons as a guide to what we might expect or anticipate or be interested in when we look at exoplanets and eventually their moons. We should be cautious because it's possible that our solar system is not completely typical, and we've already seen some indications where exoplanets have quite different properties from any of the planets in our solar system. But we believe the processes of planet formation and moon formation are universal, and so we can draw some general conclusions. We'll look at the basic layout of our solar system, the characteristics of the inner planets, the characteristics of the outer planets, and then a comparison with the exoplanet systems found so far. In broad brush terms, our solar system is composed of the central star, the Sun, comprising 99.9% or more of all the material, and composed almost entirely of hydrogen and helium, the 4 terrestrial or rocky planets, and the 4 Jovian or gas giant planets. And there are quite a segregation in properties between these two classes of planets that we believe is associated with their process of formation. Starting in the inside, we have Mercury and Venus. Mercury is geologically dead with no atmosphere, and its bare surface is exposed to deep space and the radiation from deep space. It's tidally locked with the Sun, and so one side is blasted by solar radiation from a very short distance, and the other side faces into deep space at a temperature hundreds of Kelvin colder. Mercury is almost certainly geologically dead. We have visited Mercury recently with spacecraft and confirmed that it is somewhat moon-like in its properties and appearance. Venus is the closest twin to the Earth, and therefore interesting for that fact. In fact, it's very much a geological twin, identical in mass, size, and interior structure. Venus is highly geologically active, and we believe it was subject to a runaway greenhouse effect that raised its surface temperature to its current 900 degrees Fahrenheit, a temperature at which lead would melt and paper would spontaneously combust. The pressure at the surface is 100 or more atmospheres. This is very dissimilar to the Earth, and the question arises, how could such a twin of the Earth in its global attributes have such a very different evolutionary path? Even more interesting is the fact that the inventory of carbon dioxide in the atmosphere on the Venus is about the same as the total inventory of carbon dioxide in the atmosphere and oceans of the Earth. The difference is that on the Earth, most of that carbon dioxide is dissolved in seawater, rendering it slightly acidic. On Venus, we believe that the larger amount of carbon dioxide led to a positive feedback cycle called the runaway greenhouse effect. Whereas the atmosphere thickened, the carbon dioxide is a heat-trapping gas that trapped more radiation, which released more carbon dioxide. Remember, this is a volcanic planet, and volcanoes are a primary source of carbon dioxide on the Earth and in Venus. And so the process accelerated, ending up in a smothering atmosphere of enormous heat. The larger temperature of the Venusian surface cannot be explained by its proximity to the Sun, because that's not a very large effect. The atmospheric composition also has other toxic components. There are ammonia, sulfur dioxide, sulfuric acid even, and acetylene. All of these are toxic on the Earth, although they're present in trace amounts in the Venusian atmosphere. And yet, models suggest that 3 billion years ago, before the runaway greenhouse effect, Venus potentially could have been habitable, could have possibly hosted liquid water, if not in the surface, then underground. A fascinating prospect that our twin could have been habitable that long ago, because we know the same thing about Mars. We twin the Earth and Mars, the next 2 planets further out. The Mars are not our twin in a direct sense because it's a lot smaller and is not highly geologically active through most of its history. It's probably on the edge of habitability. If water exists on Mars, it exists in subsurface aquifers or deeply buried in ice deposits of the mid-latitudes. If you put a cup of water on the surface of Mars, the temperature is so low, the atmospheric density so low, that it would boil or evaporate in a second. Earth is the only planet in the solar system that we believe can host liquid water on its surface. And it's our thick atmosphere that helped retain that water. Mars has the old cratered surface, indicating that its last geological activity was 1 billion or more years ago. And yet, models of Mars, as with Venus, suggest that 3 billion years ago, it was warmer and wetter and had a thicker atmosphere and could possibly have hosted shallow seas or oceans, making it a fascinating prospect for astrobiology. As we move into the outer solar system, the two twin gas giants of Jupiter and Saturn account for most of the mass of all the planets combined. Jupiter itself accounts for over 2/3 of the mass of all the planets in the solar system. The colors of these gas giants have often been seen in the enhanced colors of early NASA images. Their actual colors are much more gentle, pale yellows and pale browns. The surface features are not visible. Those rocky cores are hidden by deep clouds. So what you see are the outer cooler cloud belts circulating around the planet, very large wind speeds of hundreds of miles an hour on both of those gas giants. Gravity of Jupiter has been important in the history of the solar system because it's actually served to protect the Earth from impacts early on. Both of these gas giants have atmospheres composed of about 75% hydrogen and 25% helium, similar to the Sun's composition. The typical density of these gas giants is low. It's often been said that Saturn would float in water. The color of these planets, the mild colors you see, are caused by a little sulfur dioxide and ammonia mixed in with the hydrogen and helium. Saturn has obvious icy rings, but with spacecraft missions we've seen ring systems, much thinner and less easily seen, around all of the gas giant planets in the outer solar system. There's less known about Uranus and Neptune because they have not received as much direct visitation by NASA probes over the decades. These ice giants are smaller, more frozen cousins of the two gas giants, Jupiter and Saturn. Uranus has a small rocky core and an atmosphere of mostly hydrogen and helium, and a very thin ring system. It spins on its side with its pole tipped by almost 90 degrees with respect to the ecliptic, giving it enormous seasons of almost a century of summer followed by a century of winter. The reason for its large axial tilt is unclear, but it's probably caused by a collision during or shortly after its formation. Neptune has a beautiful pale blue color primarily due to the methane in its atmosphere, and it also has a magnetic field that's offset by a large degree from its orbital tilt, unlike the Earth where these axes are quite closely aligned. Neptune has the fastest winds in the solar system, reaching speeds of over 1,000 miles per hour, and its ring system is subtle and only partially complete. In this summary, we see the difference between the rocky or inner planets and the gas giant or outer planets. For the inner planets, large objects made of rock and metal with a solid surface, few or no moons and no rings. But in the outer solar system, mostly hydrogen and helium, no solid surface visible, although it appears to be interior and measured indirectly, rings and moons around all of these gas giant planets. And where do we fit in Pluto to this picture? Well, as you probably know, Pluto was demoted from the pantheon of planets in 2006 by the International Group of Astronomers meeting at their triennial convention. Until then, we did consider Pluto one of the planets in the solar system. But to be consistent and based on what was known about planets and their formation, astronomers decided to demote it to a dwarf planet. And so it's not officially one of the planets in the solar system. Why was this done? Well, beginning about 15 years ago, planetary scientists looking for rocky bodies in the outer solar system started to find large objects in the Kuiper Belt. The Kuiper Belt is a loose zone extending from about 40 to 80 astronomical units of rocky debris. Most of these are the size of asteroids, so quite small, tens or hundreds of kilometers in size, but some of them are quite large, and eventually the largest of these were found to be the size of Pluto or even Mercury, and in fact one is known to be larger than Pluto. It's also speculated when these surveys are complete, there may be as many as 3 or 4 Kuiper Belt objects found to be larger than Pluto. So for consistency, if planet definition was only based on size, they should be added to the list of planets in the solar system. This started the debate. The first object measured to be larger than Pluto was called Eris. Actually, its discoverer, Michael Brown from Caltech, thought he could name the planet himself, and so he called it Xena, and it actually had a small moon called Gabrielle. He was, however, overruled by the International Astronomical Unit that governs the naming of planets and solar system bodies and constellations and so on. They tend to be given Greek or Roman names or names from world mythology. However, the finding of a larger object than Pluto opened up the can of worms in the definition of Pluto as a planet. The other thing that was determined about Pluto using simulations is the likelihood that it was captured from the Kuiper Belt at some point early in the history of the solar system. So it has not always been at its current location. The third and perhaps clinching aspect in the demotion of Pluto was the determination, again bolstered by simulations of the formation process, that Pluto had not cleared out a zone at its distance from the Sun. So by the triple criteria used for the definition of a planet, it was demoted to the status of a dwarf planet. And now we also know of another small set of dwarf planets along with it. And we can summarize in this lecture the properties of our own solar system, which we hope to be indicative of what we might find in extrasolar planet systems as we learn more about their detailed properties. In our solar system, the inner planets are rocky. The Earth is special. Although there are other planets with magnetic fields and geological activity, the Earth is the only terrestrial planet that can host liquid water on its surface. However, models suggest that both Venus and Mars in the distant past, perhaps 3 billion years ago, could have hosted liquid water and been habitable. The gas giants are unlikely to be habitable in any aspect. They are large, composed of hydrogen and helium with internal rocky cores that are subject to intense physical conditions of temperature and pressure. Meanwhile, a third category of planets has been declared, that of the dwarf planet. Pluto was demoted to the status of a dwarf planet about a dozen years ago, and since then we found other dwarf planets, objects small enough that they were either captured into their current orbits or were not able to clear out a zone as the planets formed in a protoplanetary disk. We anticipate that dwarf planets will also exist in extrasolar planet systems, although they are currently below the range of detectability.